Hello, welcome to our channel. Today I'm going to show you two models related to deep learning steganography and concealing secrets and images. First of all, I'd want to give you a quick introduction into what deep learning steganography is and why it could be beneficial. Deep learning steganography is the art of hiding secret information within an ordinary cover image, and it's very useful in security and cybersecurity, especially in that field. I'm going to give an explanation of this code and what it does. First code is just us setting the library, the batch size, the number of epochs, the learning rate, setting our GPU to be used. But here the model is very small, we wouldn't need to release our GPU. And then we're defining our layers. The first layer here, there's three layers, but this layer is a convolution layer that calls back the rest of the layers later on. First layer is our preparation layer. It prepares the secret to put it, the secret image to put it into the cover image. And then you have the hide layer that hides the secret image into the cover layer. And then there is a reveal layer which reveals the secret image from the cover image. This is our model. We're defining it and initializing it. And then we're defining our loss function and our predictions and how we're going to call them. We're using an MSE loss here for this model. Here we're defining our secret input and our cover input, and we're defining the shapes of 6464 since our dataset has the same size of an image. This is the model summary, as we spoke before, and the number of parameters, the trainable parameters, and this is a visual representation of our model. Here we're setting up the optimizer, and we're setting up our loss and our beta so we can train the model later on. We're also saving our training into this model file, and then we're loading our tiny image set. It's called a Macy Tiny Image Net. It's a very small data set that could be easily split and trained. That's why we used it. We're using this model as a way to understand how deep learning steganography could work. Here we're splitting up our data for the training, as you can see, and here's a small data visualization of the first image in Tiny ImageNet, the Macy Tiny ImageNet. This is the data visualization of the first image in the matrices, and this is our data preparation, data generation, us calling all the layers after training, setting the batch size again, and using some of the libraries that could be used in steganography. This is us training the layer, as you can see. And then here is us testing the layer. Here we're showing the first test secret in the matrices, which is this photo. Then the first test of the revealed image. And then this is the cover image in the matrices. This is the cover with the secret in the matrices. So basically, this image is put into the cover, and then the model has this image, then it decodes the secret image to print this image, as you can see, due to loosely compression and memory loss and a lot of other factors. Some of the image color has been distorted due to pixelization and the distribution of the pixels. Here we're saving our complete model, saving our hide layer and reveal layer, and then this is some digital visual representation of our loss, and as you can see, training loss keeps decreasing in the model in general, which is good. It shows that our model isn't overfitting and it's fitting correctly and is able to predict correctly. This is a visual representation of the predicted pixel values, and these are the loss for each layer. We didn't use ROC or K-folds or confusion matrix in this project, as there's no need for it since our testing doesn't on a bigger model we wouldn't need to, because we can't really test our model like this. This model is way simpler, so it's easier to test the model, but on a bigger scale it's harder, and I'll show you later on in a second the other model that we built, which is way more complex in nature. So now we're going to show you our other model in a second. Yeah, and here we're importing our libraries, setting our GPU to be used, our core. Here we're importing our dataset, COCO, and we're giving the directories to the train and valid file. We're shaping the image into 64 by 64 for consistency. And here we're splitting the dataset into train, validation, and test. As you can see, here we're specifying the number of image for each dataset split. For the train we have 1000, for valid we have 500, for test we have 500. We're loading the split, normalizing the image vectors, printing some statistics, like the number of training examples of the shapes of the train matrices. Here we're splitting the number of secret images, and we're naming them into input S1, input S2, input S3, and taking each training set depending on how much we need. And then we're splitting also some of the train images into an input cover, printing the shape and the amount of inputs. Sorry, we kind of forgot to print out S3 too, but it's going to be same shape. Here's a data visualization of the COCO dataset and some of the images in it. Here we're setting our loss functions for this model and our beta. As you can see, this is the loss function that we're using, and this is the loss for our reveal. We're returning them here, returning the encoder as a Keras model for the preparation network. As we mentioned in the model before this, we had a preparation layer and then a hiding layer, and the same goes here, but here it's more complicated, and There's more filters to be used. However, here we don't have a reveal network. We have something called a decoder network layer that works as a reveal layer, since we're using PISR, which is related to noise. We're trying to decrease the noise here in the decoder layer. As you can see, we're decoding each secret image. That's why you have decoder 1, decoder 2, decoder 3. And then here we have the full model set and initialized with the optimizers and the loss function that we made and we're using instead of the MSE loss that we used before. And here is a model summary of our model. As you can see, can't really use a visual representation here since VS Code is having some trouble with PyDot, but we did use a Collab to have a visual presentation of our model. And this is our epochs. We're setting them depending our learning grade. So once our epoch goes through 200, we're using this learning grade. Once it reaches 400, we're using this learning grade. Once it reaches 600, we're using this learning grade. Once it's done, we're using this learning grade. As you can see here, we're training our model on 2 epochs. Here we have a visual representation of the model loss for the 2 epochs. As you can see, it's not overfitting. Then we're training it on 5 epochs. As you can see here, the loss continuously decreasing. And then we have the loss for each reveal layer. As you can see, it's also increasing for reveal layer 1, reveal layer 2, reveal layer 3. Then we're training it on 50 epochs and saving the model later on in autoencoder file. As you can see, it took some time. And then we're training it again on 700 epochs. This also took some time. Also continuously decreased in all levels of loss. Then we trained it on 400. We're saving the model here. Then we're retrieving the decoded prediction, getting the absolute difference. We're getting a visual representation of, should be getting a digital representation of our pixel loss here. We're getting some errors across each secret and the cover. This is another pixel loss visualization, and here we're starting to show some of the images clipped. As you can see, this is the cover, secret 1, secret 2, and then secret 3 cover with the encoded secrets, all 3 secrets, and then each secret is revealed. As you can see, the difference between this model and the first model that we showed is that, yes, the cover image does get a bit discolorized, and that it could be improved with less compression, a better loss function. However, our reveal layers are close to perfect when it comes to color. We didn't lose that much color, as you can see. We had some memory leak due to our GPU not being able to uh, be on for more, so our kernel crashed. But however, if someone would want to use our code, you can print the accuracies. We hope that we could print the accuracies to know how accurate each model is here. Also, printing each loss and comparing it to the model loss. Same for each layer here. And then we saving the cover images and the saved encoded images, loading them into different MPY files, and this could later on be used into testing the model. But since we didn't have more memory, we couldn't test more, and these are some plots that could be used to calculate the PSNR and MSE uh, MSE loss. However, we couldn't use it because of crashes in the code. We had a better GPU and more time to better have a better drop out in our convolution networks. Most probably we could have had these metrics used in our paper.